I'm gonna go and start going over part B because some of us are not focusing, and I noticed that I didn't have 30 views on all the videos. That means some of us either watched it together or didn't watch them at all. So I'm trying to see if you actually know what I'm talking about. So look at the first one. You have to compare the type of particle attraction, either ionic and covalent, which is intra-particle attraction, or if they have the same type of intra-particle attraction, then you have to compare their intermolecular forces. Okay, so do both of these have ionic bonding? No. Ionic bonding and then covalent, it's a nonmetal and nonmetal. So automatically you should know who has the stronger attraction. KBr, because you have a Coulombic attraction that has full charges, full +1, a full -1, and then this just has a strong dipole moment. Who cares? It's got a dipole-dipole interaction. That's not that big of a deal when you have an ionic substance present. So that should have the stronger one. These next two, covalent or ionic? Both covalent, so then you have to go say, okay, what kind of IMF do they have? Dipole-dipole, because when you drew it, you notice they had you had a lone pair on the P and the P on both sides. So both of them have the dipole-dipole interactions. All right, now we have the same interactions. How do you compare which is a stronger interaction?
Ionization. Well, no, yeah. It's not that.
You can look at the electronegativity, kind of. You can. What do you mean the atomic radius?
So they'll. Oh wait, that's.
Enter. Well, you watched the notes. What did it say for London? I mean, for dipole-dipole. Go back. First slide or second slide. You do look at the strength of the dipole-dipole attractions, but both of these you have fluorine and chlorine. Thank you. You both have fairly strong dipoles because they're both dipole moments to a halogen. But polarizability, or the ability to share your electrons even more, is a very important trait here. So who's going to have more electrons? One with a higher molar mass. Because with molar mass, you bring extra protons and extra neutrons, right? Neutrons don't do a darn thing. They just make it heavier. But with more protons comes more electrons. So who's going to have more electrons to play with here? PCl3, because it weighs more. So we have covalent all the way, we have dipole-dipole all the way, so the star of the show here is going to be the molar mass when you're comparing them. All right, next one. No. Tell me your reasoning. What was your thought process? They both have both ionic, so then how do you figure out who has a stronger attraction?
They have the same charge.
They have the same charge product, so this is a +2 and a -2 on both sides, okay? The one what?
Oh yeah.
Look at the what? So the atomic radius. All right. Who's gonna be a stronger? Who's gonna create a stronger attraction? Smaller things or bigger things? Smaller. Who's smaller? Ca. Atomic radius. Ca is up here. Va is down here. Ca is smaller. It gets closer to its partnering anion. Since they have the same anion, you look at the size of the cation. So the cation that's smaller is CaO, so the distance is smaller in accordance with Coulombic attraction law. These twos look awful. There we go. So smaller distance means a greater force. All right, Rn and Ar. Why? Because it's what? Molar mass, more electrons, and it's bigger. All those correlate with polarizability. This is the word of the day. Polarizability means that the electrons in radon, can shift around more readily than those in argon because it's got a humongous shell of electrons. It's got 3 more shells. So there's a whole lot of electron shielding going on in between. The valence electrons on the outside have no idea they're supposed to be attracted to the nucleus. So they move around a lot more. So radon has more electrons that are free to kind of shift to one side. The shifting to one side causes a temporary dipole moment, which means that it's going to create another dipole or induced dipole in the next radon particle that's right next to it, and on and on and on and on. But then like that, they can all stop attracting to one another once their electrons are back balanced. So it's still temporary, so it's still really weak. So what kind of force are we talking about here? London, but the more polarizable one is the one with more electrons because it's got a bigger shell. So that's going to have a stronger London dispersion force. Between these two, what do you have to do? Okay, so we have water and H2O2. How's that look? So O's and O's in the middle.
Yeah.
H is here, here. Alright, so who's going to have stronger... Okay, they're both covalent, right? So what IMF are we talking about? Hydrogen bonding. Okay, hydrogen bonding. Who has the ability to do more hydrogen bonding?
Yeah.
Hydrogen peroxide, right. So this one can hydrogen bond with that lone pair and that lone pair because it's the lone pairs that are attracted to the other H's on another atom, right? Because it's got the negative area. Well, this one's got double whammy lone pairs. So this one can undergo more hydrogen bonding, actually twice as much than water can. Okay? And if you were really trying to figure it out, you could even do smaller amounts. And this one does win. That's kind of a mistake, though, because it's actually the ability to attract to the lone pairs, but it actually ended up being the right answer. Yeah.
I'm just kind of confused on, like, I understand why it is, but in actuality, like, they put hydrogen peroxide in, like, the brown bottles because it always goes to that atmosphere.
No, it's because it's reacting with light. It's
Oh.
photosensitive. Yeah, it's not because it goes in the atmosphere. It's because water kept in bottles, too.
Oh.
It's not the bottle. It's the photosensitive nature. Okay, hydrogen sulfide or hydrosulfuric acid gaseous, and water.
First one.
Are you just guessing?
No.
Who can do hydrogen bonding? H2O.
Yeah.
What can H2S do?
That's not mine.
Dipole. So this one, yeah, it looks like water, but it doesn't have the ability to hydrogen bond because it doesn't have H naught. It doesn't have FO or N bonded to H. So this one's going to undergo dipole, while this one can hydrogen bond. So this one definitely wins. So, I mean, I'm going through the process. I got to do the same thing you guys could do. What is it? Ion or covalent? If it's all covalent, I interrupt the forces.
Pardon
And
the
then you
interruption. All leadership students that are to speak at this time.
name that.
Teacher cadets and cheerleaders, please
Who's
report
looking
to
at me? Anybody?
the comments at this time.
I'm videoing, so we're good.
Thank you.
What's the name of this?
Next one.
F. F.
Ethylene. Oh, ethanol. What can is it?
It's not an acid. It's a alcohol.
That's
So ethanol. This is ethanol. Okay. This is ethanol. What about this one?
Butane.
Butane. Good, because it's all single bonds. All right. So ethanol versus butane. They're both carbon chains. They both have covalent bonds. So what are we looking at? Okay, not necessarily the length. If they have the same exact structures, we have to look at the mass and the length. Right? We have two different structures. What'd you say?
Is it like
I'm looking at the
linearity?
forces. No. Thank you. This one can hydrogen bond.
Oh,
There's an OH group here on the end. So H is bonded to O. Does this one have the ability to hydrogen bond?
Mm-mm.
What is it then?
It's just dipole.
No.
Right?
London dispersion. It's not polar all the way.
Oh yeah, that's right.
All right, so London dispersion there, hydrogen bonding here. This one's definitely the stronger force. Name this one. No, it doesn't. Since it doesn't. Actually, it's hard to see that there, but it would have to show the O playing next to the C to be a ketone. So you'd see that it's double bonded to the O. I mean to the C. Ether. Ether is coming out close. Somebody told me they quit AP chemistry for Lynn.
That's a good.
Give you a hint. No? Nothing? Diethyl ether? I actually said this one on the video last night, so I was hoping. Ethyl groups on the ends, CC, CC, right? There's two of them, so we call it diethyl, and it's an ether because it's got an O in the middle. How do you remember an ether has something on both sides? An ether has something on either side. Got it? Ether is something on either side. Okay, what kind of force can this undergo?
It doesn't bond to the H's, does it?
That's what it looks like.
Yep.
Dipole, dipole. There's a mutation. Yeah. There's a lone pair on here and here. Carbons all have H's everywhere. So this right here is that part of it's going to be kind of a bent area. So it can definitely dipole on this one. What about this one? Yeah, that's pentane, London dispersion all the way. So that diethyl ether is the winner here of the chicken dinner. Okay, did we start this last one?
Yeah.
All right, I'm gonna run through some of these because I want to get to our actual notes real fast. Where are we at? Okay, so pretty much all of our physical properties directly relate to the strength of the IMFs, right? Which is the only one that has an inverse relationship or indirect relationship. Okay, volume and pressure is kind of what I'm going with. I'm asking for the physical property that comes from that. Vapor pressure, thank you. So vapor pressure, if you have a high vapor pressure, it means you are vaporizing like crazy. What is your IMF? Slow, London dispersion most likely. If you have a low vapor pressure, give me an example of that. What substance is a low vapor pressure? Does not evaporate readily. Water. If not, the ocean will be gone, right? Okay. So if water's not evaporating very easily, then it's got a high interaction with itself, which is hydrogen bonding from its electronegative dipoles. So let's just do number 2, heat of vaporization. No. Sorry, let's do number 4, lowest vapor pressure. All right, do you want to go through the process or just guess? Thank you. Okay, so in your head you're going, okay, lowest vapor pressure means doesn't evaporate well, which means highest IMF. Highest IMF means London dispersion, I'm sorry, not London dispersion. So when you're looking, you see that you got 2 nonpolars here. Nonpolar, nonpolar. Those are out automatically. This one has the ability to hydrogen bond. So this one's definitely got the lowest vapor pressure. Yeah.
On our sheet, I think the H2 is H2O.
I think I accidentally messed that up when I did that. So yeah, because I was looking at my sheet, it wasn't the same as this. So if it were this, that's supposed to be the case. If it were water here, and you're comparing this, what would you say? But it's got a larger molar mass. But no, this one still has 2 lone pairs here. But this forms a structure that allows for, this is a big methyl group. Big methyl group on the end, big, compared to the OH group. So the methyl group is hindering other ones from coming in and attracting to those 2 lone pairs. This one is not hindering lone pair attraction at all. It's like, here I am, take me. So the waters up here can readily, kind of squeeze in there and attract. So you have to kind of look at their shapes as well and their bulkiness. This one has a bulky end, which limits attraction. This one doesn't have a bulky end, which enables attraction. So I would say water, because it does have the 2 lone pairs, it's small and condensed and things can get closer to each other, which makes it less likely to vaporize. Okay, so sometimes you got to talk yourself through it. It takes it some work. For any of the physical properties?
Yeah.
Yeah, because physical properties relates to physical changes.
Yeah.
Physical changes works on IMFs. If you break bonds, you're doing chemical changes.
So for like number 1, CaO would not be the highest freezing point. It would be H2O.
It would be this one because the highest freezing point. Which has the highest, I always think of freezing point as the highest melting point. This one has the highest melting point. So, and that's because you do have to consider their solid state. Their solid states are whenever they, either they're in their solid state because of increased IMFs or they're naturally in a solid state. So, the opposite of freezing point is melting point. That's easier to think about because you're thinking about breaking them apart. And these don't break apart unless you actually, because you have to make them mobile. You guys are working on this together. So let me go ahead and do, this is the other part of yours. If you look on the other side of your sheet, you see it? Top right, that's your homework. We'll probably get to the end of class though, but I want to go through these today. Okay, quick review of metallic bonding. You already know that they have a CFD localized electrons, yes?
Yeah.
They're conductive, yes?
Yeah.
Why are they conductive? Because the electrons are mobile. Why are ionic structures not conductive in their solid state? Alright, because their lattice makes their electrons stay in one place. They're stuck. They're in a specific structure. Okay, so that's basically what we need to know about the metallic bonding. Why do I say bonding like that? It's an interparticle attraction. Okay, what's the only true bond? Huh? Covalent. Like bond is a bond where you say, okay, you hold my electron, I'll hold your electron. Okay, we're sharing electrons. Okay. But ionics are just a severe attraction. That's it. It's like extremely large attraction. This one's a pretty good attraction. Attractions are not bonds. We say bonds because it just kind of stays. We're talking about similar things here. Why do I have this scheme here? Give me your thoughts.
So because of charge?
Give me more information.
Well, if it bonds with the same anion, the charge product is higher.
What do you mean same anion? We're doing metallic bonds. There ain't no anions here.
Oh, I thought you were talking about.
There's aluminum and silver.
Okay, so what happens when this one loses electrons? What's it form? Li plus, and there's one valence electron floating around. This one, 2 plus, and 2 valence electrons floating around. Al3 plus, and 3 valence electrons floating around. How can I explain this with Coulombic law? Y charge product. What are the two charges we're talking about here? Right. So you can use Coulombic's law for anything that has a charge or a partial charge. This was on the notes from last night. You can explain anything, even like water having partial negatives or partial positives. So this right here has a 3 plus charge and a 3 minus overall charge over the distance. All these distances are going to be about the same because, as these cations they lose their valence shell. So they're all becoming about the same size. So the thing that's actually causing this attraction to be greater is the charge that the cations feel for their own electrons that are floating around. So who's going to have the highest melting point? Aluminum, because it has the highest attraction for its own cell, its own delocalized electrons. Make sense? Okay, so you can explain this using force is equal to Q1, Q2 over distance squared. Usually we don't square the distance, but that's the appropriate way to write it. Because usually we're just doing qualitative differences. Okay. Okay, alloys is the new big thing on AP. We talked about alloys in honors chem. It's simply a what? Mixture of 2 or more metals. And it can actually be a mixture of 2 metals or at least 1 metal, and you can include another, non-metal or 2. So a common alloy that we find, Dale Earnhardt Jr. is made of it, or no, not Dale Earnhardt Jr., the first one. C is made of it in Kannapolis. What's he made of? Copper. Not copper. Copper and zinc, which makes bronze, brass. They have a similar appearance. So these bronze and brass, are they elements? No, they're a mixture of metals and or other elements. So they're not actually a specific thing we would find on the periodic table. We've created this. This is man-made. Why would we make something?
It's more durable.
Okay, it's more durable. We have desirable characteristics that we can make when we put these things together. So, like, I don't like an apple by itself. I don't like caramel by itself. I like apples and caramel. Desirable characteristics, whatever you want to think of. This is all an alloy is. It's just causing something to last longer, be more durable, have a more conductive nature, be less corrosive, or be less reactive. Copper by itself, we can see that the Statue of Liberty has a sheen on it. What's that sheen made of? It's a greenish flaky stuff. What's that called? What's it? P. Patina. It's called patina. Patina is the reactive layer, or the oxidized layer on the outside of the Statue of Liberty. Learning something today. Okay. So patina makes it look that awful green color. It did not used to look like that. Okay. So it had copper in it, which was very reactive. We mesh copper and zinc together to limit copper's reactivity. Zinc is less reactive. Okay. It actually can be a good oxidizing agent. Yeah. It can be a good oxidizing agent, but it also can limit copper's reactivity once they meld their properties together. They no longer contain their original characteristics, they have a new characteristic. That's why we have pennies made out of brass, because it's not going to explode in your pocket or corrode when you wash your jeans with your change in or whatever. So there's a lot of other characteristics like that. But we're going to talk about, that was just alloys as a whole. We have to know the specific two types of alloys, and I don't know how they're going to ask these questions, so I have a couple pictures to show you. They want you to be able to identify a substitutional alloy versus an interstitial alloy. What's interstitial fluid, AP Bio people? Okay, perfect. So here's cell number 1. This is like vocab though, you don't really have to think about it. Interstitial fluid is between two things, and it's the fluid between, in this case, cells, and this helps when you're conductivity and transport of different chemicals and stuff to cells through the semi-permeable membrane. So interstitial alloys, we don't talk about cells in biology, we talk in chemistry, we talk about atoms. So this is just things between atoms in the alloy. The things specifically are usually nonmetals. So interstitial alloys have nonmetals between atom or metal atoms. Commonly, you'll see carbon is a probable interstitial atom because it's not so reactive and it has other properties that we kind of take advantage of, like high heat capacity. So a cast iron skillet, what's it made of? Iron and carbon. Cast iron, Fe, carbon, cast iron, carbon. Okay, get it. So cast iron has cast iron maintains its heat all day. Back when your great-great-grandmother was cooking food, she wanted it to stay warm all day. She started in the morning. Well, she would use a cast iron skillet because it maintains its heat. It's not the iron doing that. Iron is very conductive, loses its heat like that. Carbon actually causes it to retain its heat over time. So that's a property we desired and we put it together. I told you about the bronze and the zinc. 24 karat gold. What's it commonly known for?
Rarity and
Okay, it's pretty, but they give it to Olympians, and they can bite it, right? I used to carry that baritone home every day. My 24 karat gold ring on my grandpa gave me. At the end of the year, it was bent because it's so malleable. It doesn't hold its shape very well, so it's so soft. So now, most people don't buy 24 karat gold because it is not as durable. People will buy 16 or 18 karat gold or 14 karat gold because it's got other things mixed in it. Silver, silver, copper, nickel, which Molly can't have, a couple of other things to create that alloy that's a little bit harder and more durable. Yeah. Galvanized metals has a sheet of zinc on the outside to limit reactivity. Not an alloy, it's just a sheet. Okay, the other one is substitutional. This one's pretty easy. It substitutes in. It doesn't just sit in between. It actually says, okay, using come here, I'm putting copper in. There's a total substitution. So it's going to change the shape of the crystalline lattice a little bit. So metals do have a lattice structure. It changes it a little bit, like the size and the compressibility of it some. But the structure, the composition's changing, so we're going to change the name of it. So it's no longer just copper or just zinc. We're going to call it brass or whatever the alloy is. We do this because we want to create some sort of desirable characteristic. This purple part is strictly from the curriculum that AP said. You should be able to compare alloy properties to that of the constituting elements. So if, like I said, metal solution or metal mixture number 1 had a 900 degrees C melting point, and then mixture number 2 had a 1900 degrees C melting point, which was the alloy number 2. So it's going to create some just sort of desirable characteristic. They would have more information data for you, but that's just a quick example. Determine if an alloy has formed. So it might talk you through a process, and if there's two metals coming together, it's probably an alloy. Identify the type. So I'm thinking they'll give you pictures. So this is my picture here. I'm going to scroll down to here first. So they might ask you to pick out the substitutional alloy based on A, B, C, and D. So they probably won't have colors on it though. They'll have like dots and stripes and stuff representing different atoms. But you can see the pure metal has all the same single composition. Substituted ones have, like the third one over, they substituted out for a smaller one. So they might even ask you to identify, would that be zinc or copper or carbon, or not carbon, or like manganese or something. Yeah.
Do alloys form spontaneously?
No, you have to force it. Usually you have to create, because it's a chemical reaction. So this is a substitution one. Interstitial have the things between the atoms. You can see the difference there. And the one that has both is here. Can you interpret those pictures decently? Pictures are pretty easy most of the time, I hope. And then, I don't know if they'll do this, but they might even have like a 3D picture where they show one, like, 4 layers of one lattice, and then they have the other ones that are, is that substitution? Oh, dang, it's right there. Never mind. I was going to ask you. But you can see that it's from the same area, it's substituted a different one in. It's not interstitial. So you're identifying substitution, or you would see this one where these all are one atom, one type of atom, and then between them is that interstitial atom.
Those pictures are different.
This one?
These
You
two
can't
are?
see the colors.
Oh,
Sorry.
oh.
Yeah, this one's green. Green. Oh, I can't see that right either. Green, green, green. Do you see that color? Take my word for it. Okay.
Believe you.
Okay, there's a couple more solids we gotta go through. Non-bonding atomic solids are things that are able to form a solid, but basically because they have attractions for other atoms of its own kind. They're just atoms, they're not bonding. So they're probably gonna be undergoing some sort of London dispersion or a DD force. Things like xenon, next to xenon, next to xenon. I can actually buy solid xenon. Yes, it's a noble gas, but it's so heavy and massive that it can condense down to the solid state relatively easily. And that's because it's got the ability to disproportionate its electrons. I think I got all 8 over there. I don't know if I do or not. Its electrons to one side, which is inducing a dipole on the next couple atoms, putting all its electrons on one side. So in the end, we have a magnetic attraction. Positive attract to negative to the next atom. That's a London dispersion force. These properties that come from these atomic solids are, they're not conductive. Well, why would they not be conductive? All right, are they mobilized? No, they're still in the electron cloud. Mobilized would mean that you are free to go to Kansas and back. Huh? Oh, immobilized, thanks. So they're free to move around their own electron cloud, but they're still in their kind of designated radius. So they're non-conductive. Why low melting point? Huh? Right. So the London dispersion is the main force of attraction there. So that it's a really weak force, so it's going to be low melting point. They can break apart pretty easily. So that would be an atomic solid because it's with an atom, an individual atom. And sometimes you'll hear atomic solids used for this next one too, but I'll tell you why. The molecular solid is the way I usually talk about it because it's actually molecules coming together via their intermolecular forces. So like my best example is dry ice, carbon dioxide, and carbon dioxide. How do they interact? Forces. London dispersion, because don't those have dipole moments though? But they cancel. Their geometry allows for cancellation of their dipole moments. So overall, each of those atoms are nonpolar. Nonpolars only experience London dispersion. So dry ice has a relatively weak attraction for itself, and under such low temperatures, the kinetic energy the IMFs outweigh the kinetic energy. Kinetic energy goes way down. IMFs win. They pull it together. The London dispersion force is causing them to become that solid state. And then, so this is a molecular solid. Ice is another one. H2O. It experiences hydrogen bonding though. Solid state. These two are allotropes of phosphorus and sulfur. It's called S8 because sulfur commonly takes on 8 atoms and bonds them together in a quote-unquote molecule. It's kind of like a octetal. I was going to say diatomic, but octatomic structure. 1, 2, 3, 4, 5, 6, 7, 8. So this is what sulfur 8 looks like. You can find sulfur. You can buy it. It's yellow. It stinks to high heaven. Do you guys know what it smells like? Like rotten eggs. Thank you. Sulfur smells like rotten eggs. Phosphorus is another one of those things that they're actually atoms, but they come together in a structure that we call an allotrope of phosphorus. It can do the same thing. What kind of forces would they be experiencing with themselves? London. There's only one thing an atom can do is London. And then they have, same things, low melting point and non-conductive because they don't have mobile electrons, and they usually only experience London dispersion, excluding ice because it's hydrogen bonded. Cool. Next. Thanks. Talking to me. Okay, this is my favorite one. Okay, network. What's a network? A group. So, like when you go like to conferences, you network with people to get other contacts, so that you can talk to these people, and you know if you need a reference or you want to go work for them, whatever it is, you network with people, you talk and communicate with people. Atoms do the same thing in a network covalent solid. You've seen these, you've used them, you're using them right now most likely. Graphite. Best two examples I can give you are diamond and graphite. We're going to talk about fullerenes and buckyballs and silicon semiconductors too. Those are more complex examples. That's also new to the curriculum, so I'm going to answer your questions to the best of my ability. So network covalent solids are also called giant molecules. They all experience what kind of bonds? Bonds. Covalent, duh, because this is network covalent, right? So this is not ionic. However, it has a property similar to that of an ionic compound. It is extremely high melting point. Extremely. So this is a characteristic you usually don't see when you have just a bunch of covalent stuff stuck together. But the deal with this is it forms a giant molecule, and for you to melt that molecule or boil that molecule or whatever, it's not like, oh, here's molecule A and here's molecule B and they're attracted. No, it's like, here's molecule A. I want you to melt it. What are you going to have to do to melt that? Break what? And all that network of covalent bonds. And that's going to take a ton of energy to break all of those bonds. That's how these melt. They don't melt by pulling apart molecule A and molecule B so they can become their liquid state or whatever. You have to melt this entire thing by itself, which is why it has such a high melting point. And I'll show you some pictures of those networks in a second. So commonly you will see carbon or group 4 involved in these types because they allow for the network to form very easily. So carbon has the ability to form 4 bonds, yeah? All right, so then it's going to bond to another carbon. But then guess what these guys do? They bond to more carbons. And then they bond to more carbons. And it's like this big carbon party. And they're like, hey guys, come join the party. Okay, I could keep going. But this network has all these covalent bonds you got to break. Carbon does it, silicon does it, germanium does it. Not really tin, because tin's starting to get in that metallic kind of scheme of the periodic table. So usually silicon and carbon's what you see most often. And that's actually what you see in diamond and graphite and buckyballs. Carbon, carbon, carbon. We're going to talk about each of these though. Can I go to the next page? Thank you. Okay, cool. So diamond's my first example. So girls, if somebody gives you a ring with a carbon on it, just say thanks, guys. Appreciate it. So it's a 3D structure. One diamond is one big, huge crystal. One. It's not like, oh, a bunch of little crystals together. It's one big crystal. So that's why, like, 1-2 carats of diamonds are ridiculously expensive because it's hard to find one big, huge crystal, like in mines and stuff like that. And a lot of these are synthetically made, and I'll tell you the story about engagement rings in a second. Okay, so this is right here is a carbon, attached to a carbon, attached to a carbon, attached to a carbon, attached to a carbon, and down. So I'm just going to blow this one piece up here. Carbon, all the way around. What's the shape around this carbon?
Tetrahedral.
Tetrahedral, hybridization.
sp3.
sp3. So, are there any unhybridized p orbitals? No. So, are there any delocalized electrons? No. Can it conduct electricity? No. If you don't have open p orbitals, that means you don't have delocalized electrons. If you don't have delocalized electrons, you cannot conduct electricity. That's kind of the connecting the dots there for you. So that's pretty much what all that says right there. Diamonds form a big network, which makes them have a really, really high melting point and boiling point, but they're insulators. They don't conduct at all. So network covalents have a variety of properties. You got to really read into it to get how these properties, how you can look at a property and tell if it's network covalent or not. So if I say it's an insulator, it has sp3 hybridization, and it has an extremely high melting point, then you have to say it's a network covalent, specifically diamond. Okay, so we're going to talk, I'm going to have you identify these based on properties. So something else I want to show you here? No. Okay, so this is overly inflated in price. A couple $1,000s. Why? I can't remember the name of the company now. My husband told me this a while ago. So, like, you know, Helzberg's, Jared's, they all get their diamonds from a supplier. The supplier boosts up the price because back in 19 40s, I think, is when they started advertising. They started to say, man, if you really like this girl, you've got to give her a diamond. Have to. If not, I mean, how are you going to give her chicken? You can give her. So they started to promote that diamonds were the way to show your love. And that was the only place. That was the only way. Before that, guess what they did? They're like, hey, you like me? I like you. Yeah, let's go get married. No big deal. If you like somebody, you just got married. It wasn't like, oh, I have to profess my love to you. Here. Okay, there's no dramatic, the theatrical kind of way of saying somebody, telling somebody you're going to marry them. So in other cultures there are, but in the U.S., people said the way you have to do it is to give them an expensive piece of jewelry. Necklaces won't work, bracelets won't work. It has to be a diamond ring. Okay? So then they got all typed up, and so guys were like, dang it, I guess I got to go get this. And the girls were like, oh my gosh, this is the only way I can say yes is if they give me a diamond ring. So it's all this big talk, and then the culture shifted as a paradigm, which is a shift in the way things worked. So I can't remember the company now, but they're still active. They are artificially inflating the cost of diamonds because they know that people have no choice. Diamonds are really not that rare. Rubies and emeralds are more rare than diamonds. Yes. It's a big lie. Don't feed into the lie. I told my husband, I was like, please don't give me a ring. You're in law school. Please don't. But he did. So. Okay, graphite's my next example. This is a different type of network covalent because it comes in a 2D shape in layers. And guess what graphite can be broken by? With what? These guns, people. Look at this. I can break this. Austin.
Barely have any left.
So you can break graphite. Your paper can break graphite. Graphite is not that strong. Its layers are strong, but the interactions between layers are not. So when we break graphite, we're separating layers. So right now on your paper, you're shredding one layer of graphite across it, and it's just coming off in layers. That's it. So it's actually very soft. It does not have sp3 hybridization, it has sp2 hybridization. So it forms carbon to carbon to carbon, and then I'm just going to draw one down here. It's like a sheet, a flat sheet. And each of those carbons are attracted to other carbons, so it does form a network. However, the sp2 hybridization leaves open one important thing. What? An unhybridized p orbital. That unhybridized p orbital, I'm going to draw it here, goes up and down, and it overlaps with another one. So this top one is a sheet of carbons. This bottom was another sheet. It overlaps with ones on the bottom. So that overlap allows for electrons to jump from sheet to sheet. That's why we used electrodes, those graphite electrodes, in the battery lab, because it has the ability to conduct, and it's a cheap way to do it. So if you have unhybridized p orbitals, there's an ability to delocalize electrons, and they can jump from orbitals to orbitals because electrons are fairly energetic and they have enough energy to do so. So diamond can't because it has its atoms locked in place. It has no unhybridized orbitals. Graphite can because it does have unhybridized orbitals to work with. One second. It has a 2D structure. These sheets are mainly interacting via what? Weak force? London dispersion, which is why you can slip it right off. This is used in machinery a lot as lubricant because it's so inexpensive and it has a slippery nature and it doesn't get like gunked up, you know, like not Vaseline. I can't remember what it's called, but it gets like goopy inside of machines and kind of just stops it. It hinders the motion. This does not because it's very thin layer. Question, Raja.
Is there a double bond somewhere in that structure?
No.
No.
It's got all the carbons attached to it. It's sp3, sp2. It doesn't have one. It's got unhybridized. Can I go next page? Okay. These are cool. Fullerenes is a class of carbons that are attached to one another, 60 atoms or more. So I'll call it C60. And I'm going to talk to you guys about this a little bit as you go. So this is a new technology that's fueled by chemistry. And a lot of people are taking advantage of it, specifically medicinal or pharmaceutical companies, engineering, and energy companies, the person we're going to go visit at UNC Charlotte actually taught me a whole lot more about this on Friday last week, so I can speak a little bit better about it. But he does a lot of research with this, with oncology and cancer research. So what fullerenes are is they come in different shapes. Buckyballs have a soccer ball shape, which I'll show you right down here. That's our buckyball. It's got 60 carbons in it. Each of these carbons are bonded to other carbons. However, they have the ability to capture electrons very easily because they have so many bonds to send the electrons flowing through and jumping from atom to atom. It all relates back to the MO theory, the molecular orbital theory. And I'm not going to get into the deep details of that until like the very end. So buckyballs are used as delivery devices as well. These are nanoscale. These are incredibly tiny. They are, let's see here, millimeters, 10 to the negative 3, 10 to, so they're 10,000 times smaller than a millimeter. So negative 9 is nano, right? Negative 3 is, or 10 to the negative 3 is a millimeter. So you're 6 zeros back, so that's a million times smaller, right? 6 zeros back? No, just a group. Okay. So a really, really tiny device. However, we can create these, and we can put a flag on it that says, target your pancreas. They're like methyl groups, ethyl groups, anil groups. There's all these other groups, like chemicals that you can put on that buckyball. You put it on there and say, okay, go to the pancreas and stop that oxidation. We talked about oxidation way back. I told you that it causes uncontrolled cell death. Uncontrolled cell replication. So what was doing that though? I told you that it was bad for you. Free radicals. Free radicals have an unpaired electron. That makes them highly reactive. So it wants to steal the electron from somebody else. Well, then that makes that a free radical because you just took its paired electron, right? So it's this domino effect. It's unstoppable. Free radicals harm your body, oxidize your cells, oxidize the different parts of your cells that you need to function appropriately. So what do we eat to combat them? Antioxidants. So that's what we try to do. But what if you can't? What if you can't take in the correct antioxidants, or something that you're taking doesn't actually target the cells you want? It targets every other cell but your pancreatic cells or something like that. So pancreatic cancer is a big deal. You can target the cell with a fullerene.
Interruption. All students assisting with clubs and athletic tables report to the gymnasium at this time. Thank you.
Okay. You guys have to peace out. All right. Well, okay. Just go in 5 minutes. Okay. So after you put this stuff on here, it can target a cell. That actually can encapsulate some medicines. It can encapsulate something that's pharmaceutically created, it's synthetic. So you can implant these medicines directly to the cells you want to cure or induce apoptosis. Apoptosis is programmed cell death. You can force a cell to die if you want it to die. Do you want that to happen to all your cells? No. So these don't just get used randomly because you need most of your cells. You don't need the ones that are dangerous, like cancer-causing ones. Okay, so this is a new type of medicine, and it's a free radical seeker. It goes and takes that free radical in and causes it to come to its termination point. It can't steal any more electrons. A couple of other ones are graphene. This is our new substance that's being used in cell phones and other electronics because it's very lightweight and it's 100 times stronger than steel. You can't break it. It's one layer of carbon and you can't break it. Come on. Okay, so one layer of carbon. This is the tube shape of it. So that one layer, the DoD, the Department of Defense, is using a lot more because it's really lightweight. So you can, instead of Teflon, they might use that if it's bulletproof. There's a lot of applications in the Army and electricity conduction because it still conducts electricity. And I think that's it for this. I've got like one more thing on networks, which you guys can do this now if you want. I believe you. I believe in education first. Okay. Okay. Your sand you get in your shoe. It's hard as a rock, right? You can't even squish it. You can wash it on the sink, but it's never going to really go away. It's because it's also network covalently bound to itself, or with other atoms itself. We call it silicon dioxide, which is what quartz is made out of, and sand and glass. But technically, it's silicon tetroxide because it's got the ability to form 4 bonds with oxygens. But the shape kind of looks like this. So this is what this looks like with all the lone pairs, of course. But then there's another one right next to it. Oops, that looks awkward. But what happens is these all line up with each other, and then this silicon has 2 lone pairs on it, right? So it can actually, instead of making a lone pair, it can bond with that oxygen, and the lone pair on top can bond with that oxygen. So it ends up looking like a tetrahedral shape. So the silicon dioxide is kind of a lie as well. It's actually, it can form the 4, so tetraoxide. But this network is going to create a really hard crystal. So quartz, who's gone gem mining? Okay, it's like my favorite thing to do. So gem mining, you find all the rocks in the, well, you usually find rocks. We like to find rubies, amethyst, quartz, all the different types of quartz. I can bring in one. I have a collection. Okay, I have a collection. So I just don't like the flash years, and I'm much older than you. Okay, so these things are really hard. They don't break very easily. One thing though, you can cause them to melt with extremely high temperatures from lightning. Sand, lightning makes sand glass or sea glass, I think is what it's called, right? I don't know. It makes glass. Yeah. Yeah, we've all seen it on TV. Okay, so whenever these things react with high amounts of energy, that's a lightning strike, it makes glass, but it doesn't make it in a specific lattice or layout. It's mumbo jumbo together. It's just smushed together in a disarray. It's called amorphous. You know the word amorphous means not ordered? Do we know that? Okay. Amorphous means not ordered. So it forms a disorder of structure. And that's what glass is made of. Now glass, can it flow?
Yes.
Not if you melt it. I'm not talking about energy. Yes, over time, a glass window pane will flow. It's creeping though. It's like 50 years from now, the glass will be thinner up here and thicker down here. It can flow. So that's why amorphous is so important, because amorphous doesn't lock it in place. It has the ability to kind of slowly flow down.
So if you go to like a old house with glass windows, you'll see that. Like
Yes.
there'll be glass on the
Stick on the bottom. Okay, and I'll finish this. I'll show you guys later. I'm gonna leave. Peace out. I guess not. Go to the gym. I'll talk about silicon, and then I've spent way too long on this. I gotta show you about doping. I can finish doping tomorrow, though. Yeah, I can show you what doping is. I'll tell you guys later. All right, I'm gonna finish this with the rest of you guys. Silicon is a new. So we talked about carbon nanotubes and everything with electronics. Silicon is the other. If you don't use carbon, you can use silicon. Silicon has been used forever. So who's seen the microchip inside of their phone? Except, well, not even iPhone, so you can't actually open it very well. But you've seen a microchip. Okay, it's like a little bitty SIM card, but it's got a microchip on the inside. Okay, so the microchip is made of silicon. It's got a kind of a golden, kind of shiny look to the top of it. You know what that is? It's gold. They have gold leaves that they put on top of silicon. That creates that conductivity. So that's why SIM cards, usually if you lose it or break or something, it's expensive to replace. So silicon is really great because it has the ability to form those 4 bonds. So it can form a network covalent, but it doesn't have to. It doesn't have to form the 4 bonds. It can take on a slightly different shape or structure than the carbon version of it. That makes it really versatile. It can be used for tons and tons of stuff, specifically things that we want to conduct electricity. So we call it a semiconductor because it doesn't actually, it depends on how you arrange it. It doesn't always conduct electricity, but if you arrange it in the right way, it will. So we call it a semiconductor because it sometimes does and sometimes doesn't. That's why it's in that kind of metalloid region too, because it can act like a covalent, but it can act like an ionic occasionally as well. So an important fact about these are that if the electrons are free to move based on the structure it takes on, that's going to be creating the conductivity of it, because electrons flowing is basically what electricity is. And if you increase the temperature, what's happening? Of the electrons as well, right? Not just the atoms, but the electrons, as they move faster. Moving faster means you're more conductive. So conductivity increases with temperature. That's kind of just a logical note here. All right, so then like what they started making was titanium dioxide and silicon dioxide and all these other things that can be semiconductors, painting them on things that we want to conduct electricity, like solar panels. And that's what we'll do with that in the lab with Mr. Walter and or Dr. Walter at the NCC. All right, doping will be my last bit, and then I'll stop because I don't want to lose my people. This is the part I just had to teach myself this weekend. Okay, so what's doping in athletics? So taking things to enhance your abilities. Okay, performance enhancers. So either proteins, energy, something, I don't know, makes you last longer. So in chemistry, not from the biological realm, we're talking about chemistry, we want to enhance some feature about this chemical. In this case, it's a semiconductor, right? We want to enhance its ability to be a conductor. So we're going to dope it. We're going to dope it with either N-type doping or P-type doping. So I'm going to let you write down a little bit of this right here. Those 2 bullet points before I go further. I'm just talking to middle schoolers about science club or chem club. There's a really easy way to remember what N and P mean. I kind of highlighted it, but I got more. I made this the very first period, so the way to remember it. So microchips are usually silicon based. Silicon is expensive, really expensive, so we're trying to move away from silicon. But if you want to enhance its electrical conduction, then we dope it with impurities, like the 2 elements that are right next to it, which are what? Aluminum and phosphorus. Aluminum has 1 less valence electron, yes? Phosphorus has 1 more. Okay, let's go with phosphorus first. If phosphorus has 1 more valence electron, it's got 1 more negative to work with. Negative is N-type. So next group, N-type, negative. Let me finish this. I actually didn't even think about that.
Yeah, I didn't either, so I saw this like
Go back to the back to where all my stuff is. Put out t-shirts and stuff. I'll be right there. So next group over, which carries 1 more electron, has a negative charge. Next group, negative N-type doping. So that's going to allow it to have an extra electron to move around, right? Which is all what electricity is. But you need a place to put that. You want the electron to jump, like a stepping stone. So where would electron normally travel to? An area of positive charge. So can I create an area where there's a lack of electrons? Yes. I can create it by adding an impurity that doesn't have 4 electrons, or doesn't have 3 electrons, whatever I'm looking, or doesn't have the same number of electrons. Phosphorus has 5. So I can add a couple of impurities that have more than enough electrons, and a couple that have less than enough electrons. So P-type means it takes on a positive scheme. It's not actually positive, but aluminum, for example, has 1 less electron, so we call it more positive, and it's from the previous group, PPP, right? Previous P-type positive. So if I can have that electron from phosphorus jump to silicon and then that empty space in aluminum, that's going to allow for these electrons to flow more easily, which is inducing the conduction. So we call it a hole. If you have less valence electrons in your neighbor, you have a hole to fill. That's all what a hole is. Just means your positive area of it. So we can create junctions, and I'm going to show you the picture before I go through that. You can have a free electron here. Actually, I'm going to do it over here. You can have a free electron here on phosphorus that jumps to silicon, but the silicon readily gives it to the hole on aluminum and so forth. And so it's just these jumping electrons to fill the holes from their neighbors. So I didn't go with the right areas, but that's all it is. Inducing electrical conduction because of the junction between P-type, where am I at? this is what I'm talking about. From P-type to the silicon to the N-type, and so, or sorry, actually the other way. Negative to silicon to phosphor to the positive area. So you're just showing the jumping of electrons. And then that's pretty much it on that. The transistor is the best application of N-type and P-type junctions. Okay? We'll talk about the molecular orbital theory application of this tomorrow, because that's my last slide. How does the band theory work? So take about 10 minutes, do your homework. Do your homework for me, 10 minutes, go. You can get this done.
I got it. Think I need a new one.
Why would someone give a F for that stupid?
Guys, I just take a trick where I can get on it.
Oh, Ms. Enlow, can you
No.
have my lab notebook and my paper process sheet in it? Okay, because I just want to study, or I want to put in my study after this and everything. If I can take
No,
that out.
not right now. I need to, I need to sure to
Okay.
I'll bring it down. I'll make sure it's charged. Mercury. Maybe one more thing. What? Maybe one more thing.
Remember in the minutes, you said that. And then you showed Mercury thing.
Concave and convex, yeah.
Yeah. So then it says which one has the highest vapor pressure with, and it's between Mercury and CH.
CH what?
CH8.
Oh. And mercury?
Yeah.
Highest vapor pressure? The reason, first of all, the reason mercury forms this is that it's heavy, but it doesn't have attractions to the walls of the container. It has no adhesive abilities.
Oh.
Water forms this because it's creeping up the sides of the container because it's adhesion. Because glass has it's got the silicon dioxide in it, but it's a different type of glass that's some glass. So anyway, so the water attracts to the glass more than it attracts to itself. Mercury attracts more to itself than it does to the glass. That's why it forms a concave, and then vex shapes. But this right here is metallic bonding versus London is versus yeah.
Here when it says highest freezing point, does that mean like more positive or the highest one mean the one that's most negative?
Magnitude. Don't just do
Is that like I'm thinking about it.
Okay, think about it as I always think of these because those are hard to think about. Freezing point is you're talking about going from liquid to gas or liquid to solid, but it's easier to think of solids
freezing.
breaking. So think of it as highest melting point. Use the highest melting point.
Wait, no, freezing. Highest freezing, highest melting. Yes. No. Yes. Okay.
CO2 has the double bonds with the both of them, I know.
I'm gonna go with Nagel on that one.
Oh,
Because
let me stop videoing.